of GC. So why am I talking about GC? Well, that's actually my primal passion. When I have spare cycle to code, well, I actually write code for GC. And why is that? I believe that GC has a huge impact on customer workloads. And sometimes it has a larger impact than code generation gains. So in compiler, you talk compiler geeks and say, oh, okay, my code gen has picked up 2%, on Windows and Windows code base, 2% faster. And then you go and you make a good change in GC and you get, 7%. So for a lot of scenarios, you spend enough time in GC, so optimizing it is worthwhile. The second part is the contract that GC provides to applications is very small and crisply defined. And it enables, it's based on simple principles, and it enables us to change the implementation underneath without breaking applications. And so it's an area where it's productive to work. You're not worried about, oh my gosh, how many apps are we going to break and that sort of things. And interestingly enough, it seems controversial, but I believe that as an engineering discipline, if you like, garbage collection has been not explored very much. It has been explored a lot in research, not that much in an engineering environment where you make trade-offs and you reason about the trade-offs. And I'm going to go into this further. So I'm going to give you a very short background on what GC is, and hopefully, who doesn't know how GC works, the principle? Show of a hand. Who doesn't? So we can have more time for more questions if I can go faster on this one. Then I'm going to give a history of the development of GC in the CLR. And then what I'm thinking of in terms of problems that keep me up at night and the direction that we are exploring to solve these problems. And by the way, if you guys have questions on a particular point that I'm making and it's right on point, then don't hesitate, go to the microphone and ask. I'm not sure how much we'll have at the end left for Q&A because it's hard for me to gauge the length of the talk. So let's go to the principle. So essentially, garbage collection is an automatic memory manager. It means that people allocate explicitly by making a call, but they don't make a call to free the memory. And it's up to the system to destroy and reclaim what is no longer accessible by the program, and only this part. So basically, there are two techniques that are very opposite. So the first technique is go to first principle. What does it mean to not accessible by the program? Well, it means that you cannot find a path from the program objects, which are essentially local variable, static variable, to objects. If you find a path, then it's live. If you cannot, it's not live. And essentially, one way to implement that is to start with this static variable, local variable, and trace. Go from where they make references, and then go transitively, and essentially paint all of these objects. And then what's unpainted is garbage. So that's one way. The other one is to make your program do all the work. And that's essentially what reference counting, such as COM, does. So every operation on this object, when you acquire a new reference to an object, or when you release a reference to an object, then you call a routine as part of your program, calls the routine that actually increases or decreases the reference count that is associated with the object. And when the reference count is null, it means that the object is no longer referenced by anyone. when it's positive, it means that it could be referenced by someone. So those are actually at the opposite. One, the system does it all without cooperation to the program, and the other one, the program does everything. And actually, there are multiple variants in between, and ephemeral collection, for example, relies on some program involvement and a lot of system involvement. So I talked about engineering, and what engineers do, engineers are not there to go all out somewhere. They are there to do the best job with the minimum amount of cost. So for that, we establish factors of merit. So what are the factors of merit for garbage collector or a memory allocator? Well, there is the speed of the allocator. So what's the overhead when you allocate an object? Second one is the overhead of the garbage collector itself. And we have counters in the .NET CLR. We have performance counters, and one of them is called % in GC. That's what I'm talking about in this overhead. We also have the application pause time during GC, which affects user interactivity directly. So it's an important figure, which is not necessarily related to the time in GC, because the time in GC could be concurrent with the execution of the program. Then there is the working set for a given workload. So essentially, if you are all-knowing, at every point in your program, you should know which objects are truly used and which ones are not. But it turns out that there is a lag between the time where an object is no longer in use and the time its memory is completely reclaimed. So there is, and then there are also such factors as heap fragmentation that come into play for making the working set larger than the strict live set of objects. And then, since most of machines now have multi-core, there is the multi-core scaling aspect for all of those factors of merits. So me, I'm an engineer, and my job is actually make all of these great. That's the engineering part. And how do we do that? So let's talk about one of my favorite architecture principles is mechanisms and policy. So if you read most, I would say probably 98% of all research papers on GC, they tell you a great new mechanism. And it's so great. It collects garbage like nothing. But what they're talking about is the fact that they found a clever way to implement some policy that is in back of their head, that is generally not explicitly stated, and they implement it using a mechanism. Well, what's the problem with that? The problem is that you cannot implement another policy, and you need to have multiple policies because workloads act differently. So when people ask me, hey, is my program going to run well on your GC or not? At the end, I don't care what your program is. What I care is what's the workload. So I can look at your program, instrument it, GC does actually that instrumentation for me, and I know if you are creating a lot of temporary objects, if you are keeping a large set of static data, if that static data is being churned. And so for me, that's what I call by workload. A GC workload is the behavior of this program. And you need to adapt, to have policy to adapt when the workload is changing. And when you have essentially policy mixed up with mechanisms, then it's very hard to do. And I believe that it's a key to a long-lived implementation is to essentially keep the mechanism separate and then have a policy on top that selects those mechanisms carefully. And this way you can add new mechanisms, you can phase some out, but it's a smooth transition to your code base. So your code base essentially lives longer. So now I talked about GC architecture. So specifically, what is the GC architecture? What are the pieces that are important? And I have a very myopic view, if you like, of a GC architecture that is more modularized than what most people think about. And I'm only talking about the centerpiece here, the policies and mechanisms. And I'm excluding, for example, the problem of threat suspension. I'm excluding the problem of route scanning, even the problem of the runtime helpers that are necessary, such as the allocation helpers. And I'm also discounting the layers that interact with the OS or with the hosting layer to provide virtual memory management. So this allows me to concentrate on the essence of the mechanisms and the policies that are concerned with GCs and somewhat be relieved of the other aspects. So in the rest of this talk, I am not going to talk about finalization. I'm not going to talk about how we scan the stack. I'm not going to talk about how we suspend the E. All that stuff is actually peripheral to me, and I'm only going to talk about the centerpiece. So let's retrace from V1, and it's essentially to give you a perspective of the evolution, and then we can extrapolate forward. So in V1, we offered a choice of workstation or server GC, and it's based on a common architecture. In particular, for example, the mechanisms to allocate is the same for both. So it's MP scalable. We don't have locks for fine allocation. We have a fairly cold lock for larger allocations. But the policies have been tuned to the different scenarios. And what do I mean by this? In particular, the workstation, we want to reduce the post time, which is linked to interactive apps. Will be most seen in interactive apps. And then for the server GC, the priority was to make it MP scalable. So with that came assumptions. And the assumption was on workstation, most interactive programs have a fairly moderate activity of allocation. But having a very low post time is important. So if I had to make a trade-off in my factor of merit, I will make a trade-off so the post time is lower, but the allocation performance could be lower. On the server, however, it's different. In there, we have the assumption that the server is serving requests that are fairly independent from each other and very high throughput. So the throughput there is the king, and the post time is secondary. So that was the V1. I'm not saying that it's still the case. That's the V1. In V2, I actually, when I did the slides from memory, I can't recall much. We tuned the hell out of GC, but I don't think we introduced new mechanisms or new APIs. In V3, we actually, based on customer feedback, we found that even the low latency we had was not low enough when people were trying to render frames in real time and do work in between. So we introduced a low latency mode that turns off full GC and give you a policy that minimizes the latency. And we get latency that are sub-milliseconds with this for most workloads. For the server GC, we introduced an early notification of an impeding full collection. So the idea is that you can say, when we are 80% of the way towards a full collection, let me know. And then we fire an event, and then you can actually take this to offload the new request to another member of the same server. And then by the time the collection happens, there is no or very few pending requests in the server, and the collection goes very smoothly. People are not impacted by it. So that's in a way, that's a way to cope with the latency, that's not a way to solve the problem. That's a way to cooperate, essentially. Now, in V4, we actually introduce a new architecture for the workstation called background GC. So let's, the concurrent GC worked in such a way that when you have to do a full collection, you let thread allocate, and then you start on your tracing and the sweep concurrently while the program is going. But we can't accommodate Gen 0 and Gen 1 collection. The ephemeral collector is actually turned off during that time. And so garbage accumulates, and then at some point we run out of space and we have to stop the allocator threads from allocating. We block them until the collection is finished. So we don't provide a super small post time every time, because if the allocator is too, the allocating threads are too eager, then we block them. So the background GC allows actually two collectors to work at the same time. So you can be engaged in a full collection, and we can have Gen 0, Gen 1 activity going at the same time. And it's done in a way so the policy is not impacted. In particular, the Gen 1, Gen 0 scheduling of the collections is unaffected by this, which is actually a proof that it's good to separate policies and mechanisms. So the mechanisms there are truly separate, so it allows the policies not to interfere with each other. So that was the present. Now let's talk about what are the technology trends that we have to deal with and why they keep me up at night. So certainly we see more cores, and now very soon we'll see 8 cores per sockets. We can see 4 sockets to 8 sockets in a machine. So you'll end up with 128 cores is something that next year will be there, no question. Also, now we are working on 64-bit OS, and on server, 64-bit is what's hot. And with that, you can have as much memory as we want. And back in Redmond, we have one machine that has 1 terabyte of RAM. It's a Superdome machine. Actually, we have even 2 of them. And you can produce large heaps. And I've personally seen heap size in customer application that are between 12 and 16 gigabytes. And a full collection on a 16 gigabyte on a server hurts. So that tends to keep me at night. And then virtualization is also something that is here to stay. Virtualization allows people to coalesce their workload and be very, have smooth transition. When the workload grows, they can spread themselves on other CPUs, and it's energy efficient. It has some consequences on GC, not too much, but some. So it's something to think about. So now let's do a scorecard against the trends. So I color-coded the slides, and the green is great, nothing to worry about. The yellow is something that's coming, we need to pay attention, and the red is something that I'm working on because I can't sleep at night when I think about this thing. And so the speed of the allocator is great, and we don't see a reason why it would slow down in the future. That's fine. The efficiency of the collection itself is also good. We believe we are very, very, very competitive amongst everybody else. Now, the working set for a given workload is a concern, and then the post time for large heap is a very big concern. So the GC post time, it was such a concern that was my first priority to work on in V4, and the reason for the new background architecture. And it hasn't been deployed that much amongst you guys in customers. So I don't have feedback from you guys. I like feedback from you guys, but I don't have so far. We have internal feedback that says that it works extremely well. I believe we need more tuning of it, and that's going to happen with you guys giving us feedback. And the same approach can actually be ported to the server GC with a little bit more difficulty, but it's something that we are seriously looking at, and I hope that by V5 we will have ported the background architecture. So at the end of the day, what it gives us is it gives us a way to, if the rate of Gen 2 collection is not too high, we would be able to keep up and essentially provide all of the Gen 2 GCs happen while the program is running, thus providing low post time even for very large heap and for the server GC. People can ask me, hey, real-time GCs have been around for a while. Why don't you use it? They have really low post time. Well, yeah, the problem with a real-time GC is it introduces a severe performance problem in the execution speed. What's happening essentially is you need to block reads coming out. So when you dereference a variable, dereference a field, you need to check the state of the object and see if this object has moved last time you've seen it, because a real-time GC is based on having constant and very granular moving of objects in such a way so the moving of object doesn't impose a post time. And so that's not actually in line with the budget we have for speed execution. I mean, you can typically slow down your app by a factor of 2. So that's not something we are prepared to impose on people. So we are not doing that. So let's talk about working set. So why am I putting a yellow there? It's the fact that two things. The large object heap isn't compacted right now. And it's hard to tell, but we are actually still seeking feedback. We believe that some workloads would benefit from compacting the large object heap. Every time a customer says it turned out not to be this problem, but something else. So we still are looking for feedback on this, but we need to solve this one way or another. And we'll do it. The second is the fact that background GC itself isn't compacting. And it's a problem because the large, essentially that large heap could become somewhat fragmented. And what we do now is we detect this fragmentation, and if available memory becomes low and we are fragmented, then we will do a blocking collection at this point. We believe it's better to do that right now with the mechanisms we have. It's better to do that than force the application into out of memory or force the machine into paging, which then everything goes slow. Looking into the future, one area that looks fairly promising is since we have a lot of internal instrumentation onto workloads and onto the state of the heap. So we know exactly which part of the heaps are actually more fragmenting than others. So one thing we could do is pick a badly fragmented area that is small enough so you can actually defragment it during a Gen 0, Gen 1 collection. So we essentially add a little bit of latency into the Gen 0, which is small, so it's tolerable for most people. We add a little bit there, and we compact this area. And then we repeat on areas that are badly fragmenting. It turns out that the fragmentation is not fast and furious on most workload for Gen 2 because it takes a while for things to get into Gen 2. And by the time they get into Gen 2, we are pretty sure that the lifetime of this object is high. So we get what we call Gen 2 churning when people are using, for example, very large caches. A job of a cache is actually to delete the old piece of the cache and then add new piece. And if you look at the average lifetime of a cache item, it's pretty high. So the cache item will migrate into Gen 2 and will stay there, but not forever. it will be replaced at some point. And so it produces a churning of the long-lived object store, essentially. So doing that partial compaction is actually, is we believe, a promising way, and it's something that we are going to look into. Then if we look kind of into, long-ranging opportunities, I used to work at TI on TI Explorer, and the TI Explorer had, we bought it in one chip, which wasn't the best chip ever made, but it was a chip, and it had hardware assist for collections. And it had hardware assist when you would access memory. If that memory was indirected, the CPU didn't have to know about it, and the memory fetch hardware would actually follow this indirection and then give you the final destination. And Symbolics actually had the same mechanisms. Symbolics had a better chip. They integrated on the chip only what was very high value for them. But at the end, when the Ivory chip was executing C workloads, they were executing C workload twice as slow as a Sun microprocessor, even though they had the same transistor count and the same cost. So at the end, Symbolics lost out to Sun. And what's the reason? Well, the reason is that at that time, transistor was extremely expensive, and the surface on die was extremely was a extremely large factor of the cost, and so if you devote half of your transistors to something that is not mainline processing, then you are at disadvantage against Intel and Sun, for example. The picture has changed somewhat. Now transistors are plentiful, well, they use power, but there is more transistor than you can shake a stick at, and you cannot use transistor to speed up a single threaded application. That's becoming a problem. So now chip vendors are more interested in, okay, what are we doing with transistors? So we put more cores, we put big-ass caches, and caches are actually consume a lot of power. So could we use transistor to speed up some other workloads? And guess what? Java and .NET are becoming mainstream. I mean, I would say on the server, .NET is everywhere. So the chip vendors are becoming interested. And so we've been talking to them, and my opinion, besides lock things, is that read barriers would give us the most bang for the buck. So what are read barriers? Read barriers, I said, is essentially you want to intercept memory dereference. And if I had to do a naive concurrent compacting collector, what I would do is I would compact my objects concurrently, and then when you have a reference onto an old object at its old location, and you try to dereference, at this point I would stop the program, I would find where that object went, and I would patch the reference to the new reference, and then resume the program. And doing that in software costs too much. Doing that in hardware, if we had a user exception, essentially a branch, a conditional branch, when some condition, when the hardware could tell that this pointer is out of date. And one way to do that is to assign colors. So people are all white at the beginning, everything is white, and then as you move objects, then you say, I'm going to move object from now on, the machine color is black. But your program is still having a lot of white pointers. And so now there is a discrepancy between the machine ID, which is, it should be black, or the process, if you like. It's a virtualized execution, essentially. So, and then every time you try to dereference a white pointer and the machine is in black, then you stop. And you you conditional jump to a routine that's going to patch things up. So that's one way to do it. Okay, how about operating system assist? Well, so we've been cooperating a lot with the OS in the past to get better support for what we do. And if you guys are interested in good research paper, there was a good 1 or 2 research paper about something that looks very attractive. The idea is if part of your workload is paged out and you don't need to do a full GC, usually you need to traverse your object. And if the object is on a page that is paged out, then you need to page in the darn thing in order just to trace it. Not cool. And so if you could scroll a bit inside of your page by DOS, and the bit says, oh, I don't have any outside references, for example, or something like this, then you can cut down and you can, or I have some, then you can essentially be more conservative and not paging the object if you know what the reference set is. So you scroll the reference set away when you page out, and then that's all you have to traverse. And so the OS would tell you, hey, this page makes reference to those 5 pages, and you say, okay, we don't know which object it's making reference to, but keeping all the objects on this page can be valuable. The problem is I don't see paging scenarios. I mean, right now memory is cheap, and people stay away from paging as far as they should. I mean, on server, you should never, ever page. So this is a very interesting mechanism. However, I'm not going to push it because I don't see a great use for it. But it was interesting. It was interesting. However, we have some of our mechanisms that could be improved with more integration between the virtual memory manager and the segment manager of GC, which is where our object reside. And it could be useful for virtualization. So we would use less on an idle, mostly idle VM, we would use less memory. And it can also delay the onset of paging. Go ahead.
One quick question. Does the CLR today do any partitioning? So for example, if I have multiple cores, I can have each core have its own memory.
Okay, so you're asking about does CLR today does multiple partitioning, meaning that memory is segregated by core. Well, actually, that's exactly what server GC does. You gave a good description of server GC versus workstation. Server GC is all about providing the illusion of a uniform object space, but in fact, it's segregated by core. And when we allocate, we look at which core is actually doing the allocation, and we get memory that is affinitized to this core. And then during collection, we have 1 thread per core that goes and the thread is hard affinitized to this core, and will collect only this part. That's why we get great MP scaling. So yes, we do that. So we are still talking with the OS guys, and I can give you one example. The OS has an event called low memory notification, and you can subscribe to this event. And when memory starts getting low, this event gets raised. So it's great, and most of our servers and the GC actually subscribe to this event. The only problem with it is that it's all or nothing. It's like everybody gets notified. So it doesn't really help that much because everybody at the same time would say, oh my gosh, we need to do something now because memory is getting scared, and the I/O starts, people start to serialize their thing on the I/O bus, and the I/O bus the disk gets completely swamped, and if paging happened at this time, then you're dead. So we have been talking to the OS about having essentially per process notifications, and since they are getting better and better at actually finding out the people that are too greedy with memory, then these guys could be notified first, and then if they don't respond, then we start paging them and then notifying the other guys. So that's an area that is ripe for collaboration, and so that's one of the things we are looking in the future. Now we can go into more science fiction. I mean, things that is interesting to look at and may bear fruit in, next 5 years. And so the observation is that tracing is awesome for when you don't survive much. Temporary object, it's awesome because essentially you stop, you look very quickly at your local variables, you look at them and you trace the new objects, you get them very quickly, and then 90% of the new objects that you didn't trace, you release right away. So tracing is actually very productive, and it's productive if we have a low survival. Now, look at a Gen 2. Gen 2 is the opposite. In Gen 2, you'll find things that didn't die for a long time, so they are there. And a lot of time, they won't die ever. So, but what do? When we have to do a full collection, we go and we trace them, oh, they're alive, they're alive, they're alive. And after the end of tracing, we spend a lot of time tracing and say, guess what? We have, 85% survival. That's great. And so 85% of our tracing was overhead, right? And for 15%. So, but if you look at other techniques such as deferred reference counting, so reference counting is interesting because it is very, it has a local effect, if you like. So when a reference count goes to 0, it's this object. You don't need to look at other object. You look at this object. Now this object is dead. And then since it's dead, you can probably, if it holds on to some other object, then you can release their reference count as well. And with a little bit of luck, their reference count goes to 0. So essentially, the best case is you have just a tree, a purely binary tree, with the head gets reference counted to 0, and then everything goes down. So there is a cost to maintaining the reference count. But with clever tricks, you can actually do a loose reference counting, and they have a research paper that shows that it can show promise. So it's something that, unfortunately, it's pretty intense to write. It's not something you write on a weekend and say, hey, that looks fun. During my weekend, I'll do that, and then I'll pound on it to see if it has any chance of working. It's actually a fairly large investment to do it right. It needs to scale on MP and a lot of stuff like that. It actually doesn't solve the problem completely, because if you have cycles, then all of the objects are stuck to their reference count of 1. And so once in a while, you have to realize that you have cycles, and then you have to kick off a full collection. But it is something that I'm thinking about, and it's something that, when I have free time, I'm kind of trying to make a little bit of progress of how it would fit in our architecture. And I have absolutely no clue if it will be worthwhile. But it's these kind of ideas that I'm looking at to solve, essentially the efficiency. It's not the latency at this point. I believe I can solve the latency of large collections on large heaps with the background GC architecture, but the efficiency of a full collection isn't high. So I'm trying to raise that efficiency. So final note, you guys, in general, our customers have provided us great feedback. We got tons of workload that were problematic, that we analyzed, we solved. Either we gave a GDR or it was solved in next release. And the tuning of the policies have greatly been enhanced by customer feedback. And I'm counting on you guys to give me a lot of feedback. And we have tools, we have performance counters. Now we have ETW traces that we can collect to give us more insight when you believe there is a problem. And we are actually accessible. Maoni Stevens, who now is the main dev on GC, is spending a lot of time one-on-one with customers when there is a hint of a problem to get to the bottom of it and see what we can do in the future. So now we have 8 minutes of question and answer, and there is a microphone there if you want to go, since the session is recorded, then I won't have to repeat your question. Go ahead.
Regarding hardware assist that you mentioned, I just wondering, it's just a thought. Is it possible to somehow use hardware page faults instead? For example, if you compact into a different virtual space.
Right. So the question is, can we use hardware page fault? It turns out that we don't quite have hardware page fault, but we have close enough. I mean, it's, yeah. The problem is that a kernel transition is too expensive. So I have prototypes of this going. The problem is we take around close to a millisecond to service a page fault. And it's possible, but it's too slow.
I missed the first minute or two, and you may have covered this, but do you have any polite for the public comments about conservative GC, which has been the ongoing argument for a good 10 years now?
No, I mean, conservative GC is, for example, our collector is fully conservative if you want to. It depends on how you report the roots. We have an option when roots are reporting. We say, don't move the object, and I'm not even pointing to a middle of an object. You'll have to find the object yourself. So that's the essence of being conservative. The problem with conservative usually is the fact that you have to find roots. And exploring the entire address space to find roots is not cool. And if you look at Cocoa had reference counting. They have a lot of leaks. They decided on the desktop to enable conservative collection, and they have to actually exclude a whole bunch of the address space from being scanned. So at the end, if people store objects there, they lose, and people do. So they are. Essentially, it's the poor man. It's when people don't have an execution environment that is managed enough to find the roots, then they say, okay, fine, okay, it must be somewhere, so find them. And you know, it's inefficient at best. It's inefficient. So if we can avoid it, we should avoid it. But that's, yeah. Oh, go ahead.
Hi. As you mentioned, paging is really bad. We frequently will have like a 30+ gig process. And other than trying to be careful about allocations, are there any techniques for avoiding paging?
Yes, so part of it is actually watching the memory load. There is a get global memory EX API on Windows that will tell you return a D word called memory load. And these things will go to 100% when you are paging. Means that the memory, the RAM is fully committed everywhere, and so they have to evict things. So one technique is to actually watch this, and when you are in the 90–95%, then you start finding ways to compress your data set. And compressing the data set, for example, Exchange Server does that. Exchange Server, when they are in 90% case, they will start to empty their pipeline. So Exchange has a very long pipeline of messages that are kept in memory, and they are scanned by various filters. They are scanned for viruses, they are scanned for spelling sometimes, for politically correct words. I mean, you can add essentially custom filters. And so they have a very long pipelines. And what they do is they start to serialize their messages onto disk when they are in a 19%. And that's been very effective for them. So they are not happy because serializing takes time. However, the machine remains snappy, remains administrable, and the WMI or the PowerShell thing tells them, can report to them. So they tell the administrator that he's running overcommitted, then he needs to spread out, to scale out his Exchange server. So that's one way to do it. Go ahead.
On the 3.5 runtime, we've a certain workload that tends, we've tried the workstation, and it seems like maybe 1 out of 3 or 1 out of 2 of the Gen 2s won't be concurrent.
That's right.
So what kinds of things should we look at in our workload to tune that?
The primary problem with the 3.5 concurrent collector is the fact that the threads are allocating too fast, and so we run out of space, and then we block. And that's completely solved by the background GC. So hopefully you won't see that problem. The other one is if we are in low memory situation, like if we are in 90% committed and
I think we're the former, maybe
okay,
not the latter.
yeah, so then you're all good to go,
Okay.
before and
Upgrade.
life is happy. So
right.
try it, give us feedback.
Will do.
All right.
Just one question. You said that the issue of thread suspension was something that you didn't really want to focus on, or you didn't include it in GC. But we're getting much more kind of many core. We're getting TPL coming out and parallel link, and there's kind of a push to kind of encourage people to parallelize their applications, which will use more and more threads.
Yes.
So kind of in the idea of 64 cores or something, if you're suspending all those threads to run a GC, that seems to me to be a bit inefficient in terms of the hardware
So
usage.
Essentially, we are trying not to suspend them. That's what GC does. But the mechanics of suspension is not owned by GC. That was my point. So it's somebody else. Actually, we made progress in CLRv4 on thread suspension. We actually cooperated with the OS because suspending a thread, we need to get its context. We need to get its registers and locals and in particular where it is. And the OS wasn't reliably giving us that and without telling us that it wasn't reliable. So we are actually worked with the OS and now on Win 7. The reporting will tell us are we reliable or not. We are likely to push this fix to every OS we've made in Windows updates. So yeah, we are working on it, but it's not part of the GC source code, and it will never be. And it's modularized, and we try to stay out of each other arm length. And if I'm not calling them, they don't. Right? That's the.
Okay, I have a question in regards to sometimes I have the task of checking just to make sure that we don't have any stray pointers in our application that keeps large objects in memory. And in that, is there any way that I can tell the garbage collector to just go and do everything you can and let me know when you're done?
Yes, it's called gc.collection of 0. If you do that, we'll do the best job we can. And if there are more objects, that it's it's a problem.
But what I've noticed is you have to call. First of all, you have to do collect twice.
That's a different thing. The problem is you have finalizer. So
yes,
when you have finalizer, then you have code that needs to be run in order to finish to get rid of your object. And it's depending on the user code, you can actually have bugs where you need to run an infinite number of them because the finalizer could resurrect the object, and then you find out that this object is not dead. So when people play game with finalizations, then it makes your problem a lot harder. And right. I'm not sure what I can do because in finalization, it's user code running. I'm not smart enough to know what these guys are doing. And unfortunately, we have enough rope for people to hang themselves with register for finalization or just not even telling anybody and putting this object into a global variable and then you're dead. So the fact that I don't know what to do there.
Right, but I mean, yeah. I doubt that anybody has a really large object that doesn't have any finalizers. So I found myself
So we did something in V4 or in V3.5, which is we are trying to push people to use critical finalizers and in interop. I mean, why do we have finalizers? It turns out that most unavoidable use of finalization is when you do interop, because essentially you have your own lifetime, but you are holding unmanaged memory on behalf of your object, so you need to know when your object goes away so you can release. And what we did is we did a good job of segregating these things into safe handles, for example, Moch OS resources. And then the main object doesn't have a finalizer, just the safe handle as one. So part of it is actually trying to do this, is the main object that points to a lot of things have no finalizer, and then segregate, so make a secondary object that is dead simple, has nothing except it holds on to the unmanaged resource. That's the best we can do right now, but it helps a lot.
Okay, thanks.
Okay? All right, well, we're done. Thank you for coming and giving up your lunch.